So the next lecture in this unit is on simultaneity and the twin paradox. This is section 11.3 from your textbook, starting at page 591, where we start talking about the relativity of simultaneity. So this is a little bit of a hard concept for some students, so I'll try to explain this slowly. First I'll read this slide and then I'll discuss. So it says here, suppose you're at a Canada Day celebration and you see two sets of fireworks explode at exactly the same time, one to your left and one to your right. So that's an example of simultaneity. That's the occurrence of two or more events at the same time. So if these two things happen at the same time, when you're standing still and you see them both happen at the same time, then they are simultaneous events, or this is an example of simultaneity. Now, before we go any further, with relativity, we know that for an observer at rest, these objects would be happening at the same time. But for an observer in motion, something interesting may happen. So we'll look into this. First, let's say, looking at that fireworks example, here's a thought question. Suppose we have a car that's speeding at 80 kilometers per hour when this fireworks show is happening, and we're asked if the passengers in the car would say that they saw the fireworks explode at the same time. And in this case, they actually wouldn't, because of special relativity, and because they are moving. The idea that these events happen at the same time is only true for somebody who's in a frame of reference that is not moving with respect to the fireworks. For someone who is moving with respect to the fireworks, they would see one firework hit before or explode before the other firework exploded. So that's what this what's the special theory of relativity does to simultaneity. And here's a thought experiment to kind of look at what that to sort of explain that. So again, with a person in a rail car that's moving at a velocity of v, let's say observer 2 sees two lightning strikes hit at both ends, A and B, of that rail car. Now, the question is, did they occur at the same time? And observer 2 would say they would. But for observer 1, let's analyze this situation a little bit more. I'll read this slide here just to talk about observer 2 a bit more. So it says, since observer 2 is midway between the bird marks and the light pulses travel at the speed of light, they reach her at the exact same time. So observer 2 says they are simultaneous. But because observer 1 is moving, the light pulse from B will reach him before the light pulse from A. So observer 1 concludes that the bolts are not simultaneous. So who would be correct in this case? And the answer is, surprisingly, they're both correct. They're both correct in their own frames of reference. That's one thing about the special theory of relativity that we have to understand as well. There is one frame of reference is not better than another. There is no hierarchy of frames of reference. Each frame of reference, treated independently, as long as the laws of physics are treated are followed in that frame of reference, then that frame of reference is correct. So both observers are correct in their own frames of reference, even if their observations are different. So the observation of simultaneity can be different in different frames of reference. And the note here says the relativity of simultaneity is necessary to make sense of time dilation and length contraction. Together, these concepts ensure that no frame of reference is preferred and that special relativity makes sense. So I'd like you to copy this down. Simultaneity is the occurrence of two or more events at the same time. And relativity of simultaneity is that events that are simultaneous for observers in one inertial frame of reference are not necessarily simultaneous for observers in a different inertial frame of reference. The note here says the whole concept of simultaneity of past, present, and future is fuzzy in relativity. What is a future event in one frame of reference becomes a past event in another. This is due entirely to the fact that the speed of light is the same in all inertial frames of reference, regardless of their relative velocities. So that's something that I'd like you to copy down as well. So here's another example. It says two stars, A and B, are equidistant from a planet P and are at rest relative to that planet. They both explode into novas at the same time, according to observer on the planet. From the point of view of the passengers in a rocket ship traveling past at relativistic speeds, which star goes nova first? So for the person on the planet, these events would be simultaneous. For the person who's traveling at velocity v and they're moving towards A, they would see A occur first and B occur second. The reason why here is that if we observe the length contraction or the time dilation that it takes for the rocket ship to travel to A, that would be less than the time to look back at B. So because our speed of light is traveling at the same speed, or even if we're traveling at v, we're still, after adding in that relativity factor, the speed of light still remains constant. The light from A would reach the rocket ship before the light from B. And that's what would cause A to nova first and B to nova second for the observers in the rocket ship. So another concept here that is a bit related to simultaneity is the twin paradox. And this is something that's pretty well known in physics. It's kind of branched out into into popular physics. And this is the idea that a person who is traveling at near light speeds will age less than a person who is traveling slower than them or relatively slower than they are. So this slide here says, with this understanding of space and time as properties that are both affected by motion, comes the challenge of keeping track of what happens in each frame of reference. A famous example of this is the twin paradox. And it's kind of shown here in images. Let's read through here. It says, consider an astronaut who travels to the Sirius star system, which is 8.6 light years from Earth. If his spacecraft travels at 90% of the speed of light, that means he can reach the Sirius system in about 9.6 years, or do a complete round trip in about 19 years to go to Sirius and back to Earth. Now, on Earth, let's say his sister is working and tracking his health. The scientist's observations indicate that he is aging more slowly than he would have on Earth. In his frame of reference, he wouldn't experience that at all. So on Earth, if they're measuring the time he experiences, it would essentially be that they're measuring his time as less than 1 second per second relative to Earth seconds. And this is because he's traveling close to the speed of light. The time he experiences is still the same. But the time that is observed by his twin on Earth will be almost as if he's moving in slow motion. So now it says, during the 19-year round trip, the crew notes that he ages only 8.3 years. However, from the astronaut's frame of reference, Earth recedes from him at a rate of 90% of the speed of light. He therefore expects everyone on Earth, including his sister, to age only 8.3 years, while he ages the 19 years. So if he started to do some calculations, he's moving, he could argue the Earth is moving away from him at the rate of 90% of the speed of light. So he would say that people on Earth are going to age only 8.3 years, whereas he's going to age the 19 years. But when he comes back, he notices that it's in fact wrong. He aged the 8.3 years. His sister aged the 19 years. So there is an error in the interpretation of this astronaut. And to understand this, we have to consider that the astronaut moved in a frame of reference that was not inertial. There was an acceleration to get him to 90% of the speed of light. And during that acceleration, his frame of reference was not inertial. Because of that change, that causes his time experience to be less than that of the time experienced back on Earth. The note here says there is a relativistic observation that the astronaut can use that completely reconciles the imagined paradox. If you remember the interpretation of the muon decay in the atmosphere. So that muon experiences its time at its certain lifetime length, which I can't recall exactly what that length was. Regardless of how fast it's moving, it will still experience the same time. The observers would experience it at a different time. So in this case, the astronaut who is traveling, he's actually traveling less distance to Sirius than the 8.3 years because of length contraction. He's experiencing less time because of time dilation, and that's happening again when he returns backwards and goes the same way back to Earth. Whereas there is no experience of time dilation or length contraction for the Earth. So from the astronaut's frame of reference, this is just going to explain what I said just previously. The universe undergoes a length contraction. The distance that he must travel each way is now 3.7 light years, not the 8.6. The astronaut sees his mission take only the 8.3 years, whereas people on Earth would have aged 19 years. So this is how these two twins would end up having, they would be born at the same time, but they would have experienced different times being alive. The one who had traveled at the 90% of the speed of light, is now younger because time dilated while he was traveling at 90% of the speed of light. So copy this slide down for the twin paradox. I'm going to pause to do that. So here it says time is often thought of as a fourth dimension. And we've kind of seen that with time dilation. So we experience time as a dimension that's always going forward. We can imagine it as always going forward at 1 second per second. But with time dilation, we know that time can actually slow down. We don't know a way to go back in time. Time still goes forward only. But we can consider it as a dimension based on the idea that space and time have to exist. They have a connection to each other. They exist together. So it's another way of something traveling, not through space, but through time, or space-time. So we can consider objects have these four quantities. They have length, width, height, and time, in terms of if we're saying where an object is. Strangely, when objects move at speeds near c, space and time become interchangeable. A loss in space is accompanied by a gain in time. Events look smaller but last longer. Time cannot be thought of as independent of space or vice versa. This is why we have that space-time, because when that length is contracting, we have this increase in time. So imagine you're on a spaceship moving away from Earth at 80% of the speed of light. Your pulse, your shoe size, would you notice any change? You wouldn't, because in your frame of reference, which is an inertial frame of reference, you would notice no change. However, for an observer watching from Earth, they would see your pulse slowing down, and they would see your shoe size decreasing. So that's the concept of the twin paradox, or rather, I guess you could say the twin paradox, or this is another way to look at the special theory of relativity. For the observer who is moving, their observations in their frame of reference would typically be proper to them. For an observer who is at rest or who's moving relative to them, they would see this time dilation and the length contraction.